everything that we've done up until this point uses the ideal gas law, which is only true if the assumptions that we made in the last video are correct. If you have no attractions or repulsions between molecules, what you have is an exactly correct prediction from this equation. You have an ideal gas. So an ideal gas is a gas that exactly obeys this equation. Now, real gases don't. They deviate from the ideal gas law just a little bit, not too much. The ideal gas law is pretty useful at moderate pressures and temperatures. It explains the behavior of gases pretty well, but there's a deviation with real gases. Real gases have pressures slightly less than what would you predict the pressure would be ideally. So you would predict the pressure if you divided both sides of this by V to be nRT over V. But the actual pressure that you measure in real life is a little bit less than that. Why? Here's the wall of a container. And here's an ideal gas molecule, which is very tiny. It will have other ideal gas molecules around it, but it won't see them if the kinetic molecular theory is correct. It'll move independently of them, and it will go and it will hit the wall and bounce off and exert a little bit of pressure, and that's actually where pressure is going to come from. Now, how is that different from a real gas? In a real gas, you can have molecules that attract each other. For example, if you've got a couple of water molecules, we've seen that there's a negative end and a positive end on the water molecule. The negative end, the negative oxygen, can attract the positive end on another water molecule. They can make a hydrogen bond here. So there can be an attraction. Now what if you had molecules that were real, and this molecule is wanting to go and slam against the wall the same way the ideal gas molecule did, but it's going to be able to do so a little bit less because these other molecules that are around it, that are behind it, are going to be pulling it back away from the wall. If it's very close to the wall, there'll be more molecules on this side of it than this side, so it'll be pulled a little bit away from the wall and it will soften the blow that it has. There's less pressure due to intermolecular attractions. You might be saying, well, why do we spend all this time learning how to calculate something with an equation that's wrong, that doesn't take this into account? Well, if we look at the error in the pressure, we can relate that to the strength of the attractive forces. So you can use this model's failure to figure out something new. How strongly do molecules attract each other? Now another assumption is that there was no repulsions. Now if you've got molecules that are very close together in a box, you're going to see effects from this. So suppose I have some ideal gas molecules in a box. Their free volume is the container volume. They can go anywhere in the container. They don't exclude each other at all. They're mathematical points, right? They're negligibly small, so they can go anywhere in the box. So you'd say V is V of the box. But with a real gas, the molecules have got a small but non-zero volume. Now these molecules can't move right on top of each other. They're like a box full of basketballs. You can't push two basketballs into the exact same space. They resist, they repel. So there's some repulsions due to this. And the free volume for the real gas is not going to be equal to the volume of the container. In fact, it'll be the volume of the container minus the volume of the molecules themselves. They sometimes call this an excluded volume. So we could take our ideal gas law and correct it for these two things. We can correct the pressure for attractions, and we can correct the volume for the excluded volume that we have here. And you'll get a fancier equation. It'll be harder to solve. It'll look like this. Now, there's different ways to model the attraction correction and the excluded volume. It turns out that a good attraction correction looks like this, where A is a little constant that turns up and down the strength of the intermolecular attractions. And you can model the excluded volume like this, where B is a little constant that has to do with the volume of these molecules per mole. And then if you multiply moles times the volume that's excluded per mole, you'll get that correct value. So if you use this for the attraction correction and this for the excluded volume, you get a better equation in the ideal gas law. It's called the van der Waals equation. Now, I don't need you to remember the van der Waals equation or these correction terms. What I'd like you to remember are these pictures, because they tell you why a real gas doesn't behave the same way as an ideal gas sometimes. When do you have to worry about the size of these corrections? When is the size of these corrections going to make a big difference? Real gases behave most like ideal gases when there is lots of space between molecules. So you'll have low pressure, if you've got a very low pressure, you're going to see that things are going to behave a lot more ideally. And that is what to look for. If you've got low pressure, your real gas is going to behave like your ideal gas. Let's take a quick look at a graph. I'm going to put pressure on the x-axis, and I'm going to put PV over T on the y-axis. Now what should PV over T be? Well, PV equals nRT, right? So PV over T should be N times R, which is a constant. So for an ideal gas, I should get a graph that looks like this. The constant there, it's going to be the same everywhere, is Nr. If I put a real gas like oxygen in there, I get a graph that looks like this. And I don't really see a big problem until I get to really high pressures. So we're talking about hundreds of atmospheres here, say. What I'll see is that it agrees pretty well, the real curve for oxygen agrees okay at these lower pressures, but it kind of dips down a little bit, and then it starts going up. So you can see the deviations from ideal gases, how they work. At higher pressures, you're getting this kind of effect happening to you. Because when you have higher pressures, you don't have much room between the molecules here. And at lower pressures, the gas molecules are so far apart they can't attract each other. Here you're seeing a temporary drop in the pressure because of this effect. So down here, the gas molecules are not interacting very much because they're so far apart at low pressure. At higher pressures, you start to see this happening where the pressure is softened by the attractions between the molecules. And then when you really cramp them together, they start to repel each other. They start to exclude a volume around themselves. And you see the pressure go up higher than what you would predict. So, if you've got a low pressure, you're gonna see more ideal behavior. You also see more ideal behavior if you have a very high temperature. Why? Well, they don't really get a chance to interact. The molecules don't really get a chance to interact if they're moving very quickly. At high temperature, you have very fast moving molecules, we said in the last video. And if they're moving by each other very fast, they can resist each other's attractions. It's kind of like you're in a car going 60 miles an hour down the road, and someone's in a car in the opposite lane going 60 miles an hour, and you're trying to hold a conversation. You're only going to be able to bark out maybe a few words before you pass each other. You're not going to have much of an interaction. So, if you've got low pressure or high temperature, it ramps the attractions down, the interactions down, and you see more ideal behavior.